All right, so in the last video we were talking about two cops with stopwatches that were recording where you were at a particular time and at another particular time. I didn't actually mention in the last video, the walkie-talkies, you would need that to communicate exactly when the person crossed each position. But the long story short is what we noticed is that the average rate of change between those 2 points in space and time where the cops were looking at the stopwatch, you could compute that average rate of change, that average speed, and what we saw was that there were points along the function where the tangent lines had the same slope, where the derivative would have evaluated to the same number, the same slope, as the average rate of change. And the idea behind this is actually referred to mathematically as the mean value theorem. So what does the mean value theorem say? The mean value theorem says that if a function f of x is, and it has to be two things, if a function is first continuous on the closed interval a to b. So we know what this means. A function to be continuous has to be hole-free, jump-free, asymptote-free between A and B. And you can see that the graph that I articulated in between here, this blue graph, is just that. It is hole-free, it is jump-free, it is asymptote-free. So if your function is continuous and, moreover, differentiable, and this would be on the open interval a comma b, so differentiable everywhere between a and b. We're not going to concern ourselves with the differentiability at a or at b, because in some sense the cop really may not know what your speed was before you arrived, but they could then be concerned about what your speed was after you passed. Because if you think about it, if the cop started measuring speed at that, or your position at that instant, the other cop stopped measuring your position at that other instant, you can really only have information about speed between those two increments of time, and this relates to the differentiability. So all we're going to demand here is that the function is differentiable, to say in particular it has no cusps, there's no abrupt change in slope, right? Because to be differentiable, you have to be not only continuous, but also with no abrupt changes in slope, which is to say you have a smooth function. But this blue thing that we drew here was a smooth function. In effect, what we're guaranteeing is the case with the differentiability is that every point along the way in between, you could compute the derivative, which is to say this f prime of c would not be meaningless, because were the function not differentiable, you couldn't even say something about the derivative. But if your function is continuous, no holes, no jumps, no asymptotes, if your function is also differentiable, no cusps, no corners, no sharp changes in slope, then the conclusion that we had in the previous video holds. So the mean value theorem says, if you have a function hole-free, jump-free, asymptote-free on the closed interval AB, and if you have a function where the derivative is well-defined and exists everywhere, if you have a function with no harsh changes in slope on the open interval A to B, then the slope of the line between the endpoints is equal to the derivative, in particular, for some c between A and B. Which is to say, there's some point along the way where the slope at that point, where the tangent line's slope would be equal to the average slope, which is to say, from the perspective of the cops and pulling you over, if the cops have your average speed at 80 miles per hour, they can't say that you are going 80 the whole way between them. But what they can say is at some instant, there was some moment of time between A and B where you were going 80 miles per hour. And well, they write you the ticket.